This is the JYE capacitance tester kit. I bought this little kit in July of 2016 for under $20, $16.60, and I really do like it. It works or measures better than my LCR meter, and works down to a low range. This is marked 16. This little capacitor here is marked 16 picofarads, and let's see. Get that thing in there. Okay, it's reading approximately 17.918, which is probably about right. The capacitance of the leads also contributes a little bit. I've been trying to think of something interesting to demonstrate the capacitor, and what I've come up with is to measure and compute the permittivity of a dielectric. Specifically, I'm going to attempt to compute the permittivity of a PCB board. Let me move this out of the way for now. And here's a PCB board. Should be called a UCB board because it's not printed yet. It's unprinted, an unprinted circuit board. The permittivity of a parallel plate capacitance depends upon the area of the plates and also the separation of the plates, as well as the properties of the dielectric that separates the plates. So I've measured here the width of this plate as 101 millimeters. Let's see. The height appears to be 77 millimeters. So let me write that down. (101 millimeters by... Those red pencils are absolutely hopeless. By 77 millimeters. And we'll be expressing area in meters squared, not millimeters squared. Meter squared, of course, is 1/1,000,000th of millimeters squared. Now the separation is a little harder because it's so thin. I need to turn the soldering gun on. Soldering iron. Excuse me. All right. So I'll put my millimeter ruler up against the edge. And it's very hard to tell exactly how thick the plate itself is. I mean, what is the dielectric and what is the width of the plate? They're very thin, the plates. I'm going to say 1 1/5 millimeter. 1 millimeter and 1/5 of a millimeter. I'll write that down. And again, as meters, that would be divided by thousandths. So at this point, the only other thing we need to know, well, we need to know a physical constant, which is the permittivity of free space, and that's a number that's well known, 8.854 times 10 to the minus 12th. But the other thing that we need to measure is capacitance, because we're basically using the formula for parallel plate capacitance and turning it backwards so as to estimate the permittivity of the medium, the dielectric, from the known capacitance, which is, you know, kind of a backwards application of the formula. So I need to put a connector on this thing so we can measure its capacitance, and I'm visualizing that we'll be putting the thing somewhere like that. No, maybe like this. No, I think I'll do it this way. So let me just put a little mark on here. And these headers, these header pins fit into the socket here on the capacitor tester. So let me just break a couple of header pins off. Okay. And the short side is the pin, the rounded pin that fits the socket. I think it's the short side. Well, let me feel that. Yeah, it feels snug enough. So I'll stick this on here and solder it. Well, it's kind of hard to get that to sit still where I want it. How about that? Okay. Let's clean the desk off. I can't find anything. Alright, here's the solder. Well, I'm making a mess here. I'll put this back on and then heat it up. Okay, let's try that. The other side should be easier because once we get one side on. Okay. Not great, but it'll do. That's pretty much the story of my experimentation. Alright. This might have gone a little better if I'd cleaned the foil off. Soldering iron doesn't seem to be very hot this morning. Well, anyway, there we go. Let's see. Turn this back on. if the capacitance meter doesn't zero itself, you can push a button over here and zero it. So that's not a problem. Alright, see if I can get this to go on without shorting something. Yeah. It's jumping around a bit there. Looks like it's anywhere between 245 and 250, 244 and 250. Well, there's some more extreme, occasional more extreme values, but I'm going to say halfway between 244 and 250 maybe. The thing is, I could play this video and calculate an average, but that's a bit extreme. So let's just haul this out here and get it out of the way. And I'll write down that value. So I'll say that it's okay, 244 to 250 is 247 picofarads, which is equal to 247 times 10 to the minus 12 farads. And this up here is going to be 1.2 times 10 to the minus 3 meters. And this will be 7777 times 10 to the minus 6 meters squared. Now, the formula for parallel plate capacitance is it's A, the area, divided by D, the separation distance, multiplied by the permeability, which is usually expressed as a number K times the permeability of free space, which is epsilon naught. And as I said, epsilon naught is equal to 8.854 times 10 to the minus 12. Okay. And what we're going to do here is turn this around and basically solve for K. And then after we do that, I want to compare it to a published value and see how close we get with it. So K would be multiplied by D, CD, and divide by A and divide by epsilon naught. So that's what K would be. And I'm going to do this calculation with the video stopped so as to avoid serious embarrassment, and I'll be back. Alright, I took no chances on the calculation. Went into my Raspberry Pi and put the formula into Wolfram Mathematica, which is free on Raspberry Pi. Really neat. Well, neat is an understatement. It's like, without peer, one of the most fantastic applications in existence. Anyway, I put the formula in there, and this is what I got, 4.3 for K. And then I compared this to a published value, Wikipedia, and the published value was 4.4, so pretty close. And the material might not be exactly the same, and also our measurement of width was not, terribly precise. So 4.3 versus 4.4 is pretty good agreement. I will attach an image of the calculation after this video, and I hope this has been fun.